Okay, for this chapter, we only concern with linear partial differential equations, where this linear partial differential equation can be solved using the method of separation of variables. Okay, for separation of variables is used to solve equation that can be expressed in separable form. So it means that if the function of u is in terms of x and t, so we can find the solution in the form of a product of function of x and t. So with this assumption where u is equals to x and t, we can reduce the linear partial differential equation in two variables of 2 ODE. So the first one is we can find the first order of partial derivative with respect to x, where if we differentiate this with respect to x, you will get x prime t. And if you differentiate this with respect to t, you will get x as constant, and differentiate t, you will get t prime. And the second one is if you differentiate du over dx with respect to x, you will get x double prime t. And then if the differentiation of du over dt with respect to t, you will get x t double prime. Okay, now let us try this example using the separation of variables. Find the solution of the heat equation del u del t equals to k squared del squared u over del x squared. So we notice that u, which is the dependent variable, depends on the independent variable, which is x and t. So this can be written as into the separable form. So you can write it as x t in terms of t. So if you want to substitute this into the PDE, you have to find del u over del t and del squared u over del x squared. So del u over del x is equals to x bar t, and del squared u over del x squared is equals to x double prime t. And for del u over del t, when we differentiate x and t with respect to t, you will get x t bar. Okay, so from here, we can substitute all this function into this PDE, where del u over del t is equals to x t bar, which is equals to k squared del squared u over del x squared is equals to x double prime times t. So now we want to make sure that both sides of this equation are equal to the same constant. So we divide equation 1 with k squared xt. So we get xt bar equals to k squared x double prime t divided by k squared xt, and the right hand side also divided by k squared xt, and this becomes t prime over k squared t is equals to x double prime over x. So we get the right hand side depends on the x, and the left hand side depends on the t. So both sides of this equation are independent of x and t. So each side of this equation must be a constant. So we let this equation as equals to E. So if we solve this, we can get two separate equations, which is for the first one, this will be t prime equals to k square pt, and the second equation will be x double prime equals to x. So if we rearrange this, we will get t prime minus pk square t equals to 0, and x double prime minus px is equals to 0. Okay, now we want to solve this, but we have to we have to consider three possible cases for p. The first one is when p is greater than 0. The second one is when p is equals to 0. And the third one is when p is less than 0. So we have to consider these three. Okay, and I will show you all these cases, how to solve all these three cases. Okay, now we are going to solve the first case is when p is greater than 0. Okay, first we let p as equals to lambda square. So since p is greater than 0, lambda is also greater than 0. So now we substitute the value of p, which is lambda square, into this equation. Then we get x double prime minus lambda square x is equals to 0, and the second equation will be t prime minus lambda square k square t equals to 0. Okay, now we have the second order of partial derivative, and this is the first order of derivative. And for the second order, we can solve this using the solution, using the method in chapter 3 that you learned before, where this can be represented as m square minus lambda square x is m to the power of 0. So this will be equals to 1. So this will be equals to 0. So now we can solve m square, where m square is equals to lambda square. M is equals to positive or negative lambda. So since this is the distinct real roots, we can write the solution as x equals to, and write it as x equals to AE, where M1 is lambda x, and the second one B, e to the power of negative lambda x. So this is the equation for x. Now we want to solve the equation t, where if we rearrange this, you will get t prime is equals to lambda square k square t. And t prime is actually equals to del t over del small t is equals to lambda square k square t. And if we multiply both sides with dt, and this is also dt, you will get this will be del t equals to lambda square k square t dt. If we bring this t to this left hand side, we will get del t times with 1 over t is equals to lambda square k square dt. Okay, now we want to solve this t by taking the entire derivative of this. So 1 over t the integration of 1 over t is equals to ln t, and this will be equals to lambda square k square t plus c. So we want to solve only for t, then we can multiply both sides with exponential, and we get this will be exponential of lambda square k square t plus c. Or we can rewrite this as e to the power of lambda square k square t times with e to the power of c. Since this is constant, so we substitute this as c e to the power of lambda square k square t, where c is equals to e to the power of c. So now we have solved the equation for x and equation for t. So in order to get the solution of u, because we know that u is equals to the product of x and t, so we can get the solution of u in terms of x and t by multiply x with t. So we will have a e to the power of lambda x plus b e to the power of negative lambda x, which is this is the solution for x here, and t is equals to c e lambda square k square t. Now we expand this, you will get ac e to the power of lambda x plus lambda square k square t, and the second one will be this bc e to the power of negative lambda x plus lambda square k square t. Or we can simplify this constant as d e to the power of lambda x plus lambda square k square t plus e to the power of negative lambda x plus lambda square k square t, where t is equals to ac and e is equals to bc. So this is the solution when p is greater than 0. Now, the next one I'm going to show you for case 2 where p is equals to. Now we proceed with case 2, which is p equals to 0. So substitute p equals to 0 into the equation, we will get x double prime is equals to 0 and t prime is equals to 0. So if we rewrite this, it is actually d square x over del x square is equals to 0. So the antiderivative of this equation will be del x over del x is equals to the integration of 0 with respect to x. So the integration of 0, you will get 0, but you need to add the constant, where I substitute the constant as a. I represent the constant as a. And then the next one is you have to find the antiderivative of this, and you will get x, which is equals to the integration of a with respect to x, and this will be ax plus b. Same goes with t prime, where you need to find the antiderivative of t prime. So this will be equals to the integration of 0 with respect to t. and this will be t, which is equals to a constant c. So the next function of t is equals to c. And the next step is taking uxt, where this is the multiplication of x and t, and this is equals to ax plus b times with t, which is c, and we get acx plus bc, or we can represent ac and bc as fx plus g, where f is equals to ac and g is equals to bc. Now we proceed with case 2 when p is equals to 0. So when p is equals to 0, we get x double prime is equals to 0 and t prime is also equals to 0. So this will be m squared is equals to 0. We know that m will be equal to 0. Since it is equal real roots, then the function of x will be equals to a plus bx times with e to the power of mx. But since m is equals to 0, this will be equals to 1. So we have the function is equals to a plus bx. Okay, for t prime, we know that t prime is equals to dt over dt equals to 0. So to find the antiderivative of this, we know that the antiderivative of dt with respect to t is equals to 0 dt. And this will be t, which is equals to the integration of 0, you will get 0, but you have to add a constant here, which is equals to c. So the function of t is equals to c. The next step is you need to multiply, or you need to get the equation of u, where uxt is equals to xx tt, where x is equals to a plus bx and t is equals to c. So if we multiply this, we get ac plus bcx, or we can represent it as d plus ex, where d is equals to ac and e is equals to bc. Now we proceed with case 3 where p is less than 0. For this case, we let p is equals to negative lambda squared, where lambda will be greater than 0 in order for p to be less than 0. Okay, so from here we can substitute p with negative lambda squared. So we get x double prime plus lambda square x equals to 0, and for t it will be t prime plus lambda square k square t equals to 0. So first we solve x, where we substitute the second order with m square, and this will be plus lambda square equals to 0, and this will be negative lambda square. So m will be equals to the square root of negative lambda square, or we can write it as positive lambda I and negative lambda I. So since it involves the complex root, the equation of x becomes e to the power of alpha x a cos beta x plus b sine beta x, where alpha here is equals to 0 and beta is equals to lambda. So e to the power of 0 we get 1. So a cos beta is lambda x plus b sine lambda x. Okay, the next one is solving t equation. Okay, where t prime is equals to negative lambda square k square t. So if we expand this is actually dt over dt equals to negative lambda square k square t. And if we multiply both sides with del t, we get del t, and we bring t to the left hand side, we get 1 over t equals to negative lambda square k square dt. So to find the antiderivative of this will become ln t equals to negative lambda square k square t plus c. Then t is equals to e to the power of negative lambda square k square t plus c, or we can rewrite this as c e to the power of negative lambda square k square t, where c is equals to e to the power of c. Okay, now to get the solution of uxt, for case p less than 0, it is equals to x times with t, where this becomes a cos lambda x plus b sine lambda x times with c e to the power of negative lambda square k square t. And then this will become t cos lambda x and plus e sine lambda x times with e to the power of negative lambda square k square t, where d is actually equals to ac and e is equals to the constant of b times c. So to summarize, there are 3 cases that you need to consider, where the first one is when p greater than 0, p equals to 0, p less than 0. So each case you will have their own solution. Okay. The next thing is you need to do is you can check if this solution 1, 2, and 3 are this function is the solution to del u over del t equals to k squared del squared u over del x squared. So first you have to differentiate u with t and find the second order of partial derivative with respect to x. And if it's equal with both sides, or what I mean is if left hand side is equals to right hand side, then this solution is this function of u is the solution to this equation.